Today's agenda for this session is to continue to look into hardware of computers, and then we will switch from hardware to software, how this software actually is managing this hardware, but depending on how much time we will have, probably we will not go in much of details about software there. We will probably talk in more details about software, particularly about operating systems, which is one kind of important part of different software, probably in next meeting. So, and repetition is mother of knowledge, and therefore it is worth reviewing this general architecture of general purpose computers. So, for general purpose computers, different kind of processors may do different kind of arithmetic and logical operations on binary numbers, what these numbers represent and how exactly you do these operations, depending on meaning on these numbers, depends on some kind of software which is living in and loaded into memory of this computer. So first you get some input and either load or you may already have stored executable program for your hardware which actually describes and defines what exactly processor will be doing. And then if it needs additional input, it can get additional input from different devices and can provide different output to different devices as a result. So this is so-called von Neumann architecture. About general purpose computers, most of computers work in such way, and of course life is more complicated than that. One problem of such architecture is that if you store data and programs in the same memory, if data overwrites that part of memory where your execution instructions are located, then actually this general purpose computer can start doing something completely different. And that's one of main reasons why, for example, crackers may break into your system and start digging bitcoins on your computer, start using your computer for distributed denial of service attacks, etc. Therefore, there is another architecture called Harvard architecture, where there is distinct separation between memory, which is used for instructions, and memory which is used to handle data, like for input and output. For example, most of embedded devices are more secure in this area because they have this separation between memory, which is used to store instructions for executions, and then there is different memory which is used to handle different kind of data. And then of course this is just general idea. If we look into more details, of course life is much more complicated than that. First, we will talk in more details about different kind of buses. And bus in Latvian is kopne, in Russian I don't remember. And so these buses connects together registers of processor with cells of memory and with different kind of input and output devices. And these buses may be different, their organization may be different, ways how they send data are different, and it depends on what kind of specific architecture you have. and particularly for personal computer, there are many buses which are connecting memory with processor with external devices like hard disk and DVD disk and keyboard, etc. Usually they call about so-called North bridge and South bridge, and North means on upper part of diagram, South means in lower part of diagram. North is more expensive, faster, South is cheaper and slower, and then you usually have some more expensive buses which connects random access memory with processor, with disks and display. Particularly for display, there may be also some intermediate bus connected to it, and then there are another bus connected to it with slower buses which are cheaper and which are intended for more external devices like USB devices, Wi-Fi devices, network devices in general, etc. And then when you look, and this is everything what is inside motherboard of your computer or mobile phone or tablet or whatever. But if you look outside your system block of computer or outside body of computer, then of course there are different kind of external buses where you connect external devices to your computer. Again, they tend to be cheaper and usually also a little bit slower, but they are used to connect different kind of devices to your computer. And if you look on some old school desktop computer, so these internal buses are everything what is put on the motherboard. So somewhere here is central processor. This probably is graphical processor. Here are slots for random access memory. Here are slots for faster, more expensive devices like additional graphic card, additional hard drive, etc. So these are connected together with processor with parallel and more expensive buses. And then here when you have sockets for external plugs, there are different standards of buses used which are used for external devices. And if we are looking on processors, some of you may wonder why I can't use the same application on my iOS or Android phone or my PC running Microsoft Windows or in my smart TV set or whatever. First thing, we will go in more details about software. If your application depends on services given by operating system, then of course that application which is built on top of Microsoft Windows cannot run on top of a Linux-based operating system or macOS or iOS. And that software which uses services from Linux-based operating system cannot run in some other thing. But what is also important is that hardware also is quite different. And meaning of operating systems is that they iron out and hide internal complexities of hardware, and you may use the same Linux-based operating system on very different architecture and hardware. Not so many different architectures for Microsoft Windows, but even Microsoft Windows could run on PC compatible architecture and also a non-PC compatible architecture like DEC Alpha workstations. So, but these hardwares are different, and when you look on central unit of this hardware, which is my processor, this unit which performs number and logical operations with numbers inside it. They are two distinct architectures. One is called, in short, CISC, coming from complex instruction set computer, and another is coming and called RISC from reduced instruction set computer. And all these IBM PC compatible computers, which are mostly running Microsoft Windows operating system, these are with CISC based computers or processors which have these complex instruction sets. And probably you have heard also about architecture called x86. It comes from 8086 processor, invented and implemented by Intel some almost 40 years ago. And this standard is still used for these personal computers, which are compatible with personal computers. And of course, the same standard is used and implemented not only by Intel itself, but other companies, mainly AMD, little bit of Cyrix and IBM processors. So these are processors which makes personal computers. And historically, when compilers were weaker and not so feature-rich than they are today, this natural selection and market drive was that these computers which used this complex instruction set on computer were easier to use, and therefore they are the most popular ones. What is drawback about this is that they have much more transistors inside it. So regarding to CISC processors, Moore's law still holds. You have still exponential growth of number of transistors inside integrated schema. But it doesn't mean that performance is still increasing exponentially, because more complexity adds more speed only till it gets some saturation. And therefore, today, more and more popular, these other set of processors become popular with reduced instruction set. First, they are simpler. Second, they have less transistors inside their microchips, and they take less electricity. What is not so good about them that, for example, 20 years ago, such processors were much harder to use because you had to have good compilers, which converts your high-level programs into actual instructions to be executed inside such computer. And therefore, many years ago, these were usually used for supercomputers or some other things, like embedded devices where power was more important, less power was more important than more performance. But now these RISC-based architectures become more and more popular. For example, if some of you know something about Apple, initially they used MIPS or MIPS processors for their computers. Then they switched to Intel x86 compatible, and now they switched back to RISC type processors. For example, these new Apple computers will have M1 processor, which is RISC based. And all of mobile devices like tablets and mobile phone all have some kind of RISC based processors, because for these mobile devices more efficiency, less power used is more important than performance. But so these waves are shifting and CISC becomes less and less popular. One of the problems with CISC processors are that they are so complicated now that there are very many security issues and bugs inside the internal architecture. And so if you make your processor simpler in general, then your architecture is simpler and there are less bugs and less security bugs. So currently, usually, these RISC-based computers are only on mobile devices and specific purpose computers, but this RISC architecture becomes more and more popular. It's still, if you count about numbers of produced RISC processors and CISC processors, I think numbers are still bigger for RISC than CISC, because RISC processors are used for all small devices like Arduino and Raspberry Pi and different kind of controllers, etc. And then what is very important is that also incompatibility comes of this hardware because of two different ways how computers were built, how they handle memory. And probably you know about positional numbering of system, and if I write number 2021, I use positional numbering in decimal system in this case. So this number represents thousands, this represents hundreds, this represents tens, and this represents ones. And we use this positional numbering in such way that the biggest number is to the left and smallest number is to the right. And initially, computers started with so-called real computers, which today are called mainframes. And these mainframes, of course, used positional numbering system, and only difference is that computers are binary based, and instead of decimal, we have like everything organized in bytes. Let's say we have some hexadecimal number. No idea how much it is in decimal, but what I definitely know is that it takes 4 bytes to hold in memory. And in mainframes, when you stored this number, of course they stored it as every normal people would do. So bigger numbers are at the beginning and smaller number is at the end. But when personal computers were invented and many things were changed there just to make it cheaper and easier to program, etc. Problem is that for computers you may have different lengths of numbers. For example, this may be number with integer type, which takes 4 bytes, but there may also be number just char or byte, whatever you call it, which takes just 1 byte. And when you read and write something, you refer to cell in memory for 1 single byte, so you can't say address for single bit, but you can read and write single byte. And if you write some large number in properly created computer, like just 1, it would be 00, 00, 00, 00, 01 in hexadecimal representation. And location is this number, it takes 4 bytes, but location is shown here at the beginning where you start reading, because you start reading with bigger number. And so if you read it as an integer, you start reading from here and read 4 bytes. But if you are sloppy programmer like for IBM PC computer, and instead of writing 4 bytes you read just 1 byte, instead of 1 you read just 0, because 0, 0, 0, 0, 1 is only after 3 bytes here to the right. And so what these designers of personal computer decided is that because conversion of types from smaller types to smaller types is very common problem, and they will swap these bytes and write it in following way. So this byte comes here this byte comes here, this byte comes here, and this byte comes here. So all together it becomes something like this. And what is good about such representation in memory is that either you write 4 bytes or just 1 byte, you always will just get value of 1 back in this representation. So here you just get 1 stored inside single byte or char, depends on how it's called in programming languages. If you read 4 bytes, it still will get just 1 as actual value. And so most of real computers, like mainframes, are these big endian systems where you represent numbers in proper way, start with largest units and then end with smallest units. Most of PC-compatible computers are these little endian systems. And for example, to prove that personal computers are these little endian systems, here is small program in C, which does following. First, it declares long integer, so it's not just 4 bytes, it is 8 bytes in length. And for us to be easier to read it, it doesn't store decimal number, but it stores hexadecimal number with value 00, 01, 02, 03, 04. So what is it in decimal? I have no idea. And then it's stored inside virtual memory somewhere. Why it's virtual, I will explain it later, probably next week. And then what this program also does, it changes type, how we can look on these 8 bytes of memory. Instead of looking it as an integer number, it looks as a stream of characters, and char in standard C is in length of 1 byte. And then it goes through the loop and prints out value of each particular byte. And what happens when we execute it? First we can just run it in command line. Something has... And we see that these hexadecimal values of these numbers, if we look on this double length integer or long and print it 1 by 1, we start printing from opposite end, from here, not from here. And why is that? It's because if we would read just, for example, if here would be all zeros, and 07 at the end, so there would be no difference if I read just 1 byte or 8 bytes, I would always get hexadecimal value of 07. And we can also try to run it in debug mode. So this is decimal value of our E, but hexadecimal value of this our E is, 1, 0, 2, 0, 3, 0, 4, 0, blah, blah, blah. And you see, and this is how it looks in decimal number. And here, we are starting looking on memory from position of this variable start. And when we initialize it, what we see here, that here is place, so we can look on this memory, of course, in other places as well, but we see that here from start, we have following 0, 1, 0, 2, 0, 3, but then in opposite direction 0, 4, 0, 5, 0, 6, 0, 7. So here it shows it as a order of 4 bytes, but if we would look internally, we would see that these bytes in memory are also actually in wrong order. And so when we go through this memory and print out just one single byte, and remember in hexadecimal numbers single byte is represented with 2 characters, so we print one by one these bytes in opposite order. And so that's also quite interesting thing to know, that many of computers use positional system how to store numbers, but PC compatible computers actually store these values in wrong order. They do not mix up bits inside byte, but they mix up bytes if your number is longer than just single byte to store this value. And of course, because of that, also different kind of hardware, different kind of systems are incompatible, because this is huge difference how your computer actually works. So next thing is about memory, and for virtual memory everything is just memory, but for practical memory, of course, there are very different kinds of memory, and registers for processor are not considered part of memory for some reason, but starting from outside of registers there is this random access memory which is implemented in chipset, in electronics, and then there may be different kind of other memories. And what is important about memory is that this is sometimes called primary memory, this is secondary, this is tertiary, this is fourth, blah blah blah, etc. So usually computers try to use random access memory or primary memory as much as possible, because this is the fastest one. Also, what is problem, why they can't use just random access memory, because this is also the most expensive one. For example, for the same amount of random access memory you have to pay maybe even thousands of dollars, what may be, for example, hundreds of dollars for secondary memory like hard disk, tens of dollars for removable disks, and maybe cents, for example, for magnetic tapes, which are still used, usually not at home, but for example in large data centers, these are still used. So, and because of that these more expensive types of memory are not enough, computers usually try to decide, so if this most expensive and fastest memory is enough, they try to use it. If not, then these are used to something else. And also what is important about random access memory, particularly it is not persistent, so you switch off your computer or it lacks power, so everything is lost there. And Depending on these types of memories, we can use different ones. And this primary memory or main memory is random access, so you can read, write everywhere in it. What you say in which particular cell you start writing, in which particular address, and then you write it, and you can say start reading from this particular address and read from it. So it's something like large table of cells to hold these values, and you can start reading, writing from any place you like. Then there are also random access or direct access memory, which is much cheaper and much bigger, different kind of disk drives. In old times it was magnetic disks where you had aluminium plates with some rust on it, and then you remagnetized this rust to different directions to write zeros or ones. And sequential access is still used for large data centers, which is you write these data on magnetic tapes. And for magnetic media, you use physics in such way that ferromagnets can be remagnetized and they hold this magnetic value in one direction or other until you again apply large magnetic field to them and they may change them direction. And good thing about this technology is that it's pretty cheap. It's not very densitive. For example, you can't create large disks, small disks with huge amounts of data. You cannot create magnetic tapes, which holds huge amounts of data, very small. But good thing about this approach is that it is very cheap and it is still widely used. It's not so widely used. Probably if you have old computer, you still have magnetic disk as a persistent memory for your computer, but maybe you have switched to solid state disk already. And what is also important for these magnetic media is that they are comparatively slow, because it takes time to remagnetize these small ferrite magnets on this media, and also because of that you cannot rotate, for example, this plate of magnetic disk insanely fast. So that means that it always takes some time when you need to wait while particular part of disk is under read-write head. This is called this latency time when you need to wait. And then seeking also takes some time when you need to move read-write head around particular tracks of this disk to read and write. And we will talk in details about this maybe later, about operating system. Then of course it may become even slower, because what you consider single file in your operating system may be actually distributed in different tracks and sectors of your hard disk. It's called fragmented file, which consists of different fragments, and if there are many small fragments for large file, then of course reading writing becomes much more slower, because you need to wait additional time while head is moving over these tracks and while disk is rotating to get particular sector under reading and writing head. And physics is completely different, but idea how you write data on these direct access media is the same for optical drives. Initially they were only read-only. You stamped them out from stamp, which was created by powerful laser, and then you could only read it. But today you have read-write. Of course, times how many times you can read-write such disks is not so many as for magnetic disks. And so the lifetime is not so long, but good thing is that it's also quite cheap. You can store large amounts of data, for example, of local copies of your data for pictures, videos, etc. And of course, everything becomes we are sold slowly, and if you got some bad sectors which are not properly handled by your operating system and market as a bad sector which shouldn't be used, then of course your computer may become unbootable, or you can lose some of data. And so physics there is different, that you show coherent light from laser on these tracks, and either it reflects nicely or doesn't reflect, and this reflection or no reflection you use as a signaling for zeros and ones as a bits to save on these media. And then there are solid-state disks. Initially, these were used as a flash cards. Why it's called flash? Because it's a little bit different technology how you switch bits on and off. So first it needed to be flashed, for example, to write zeros or ones, I don't know. And then after this flashing, you could rewrite some of cells of it to ones or zeros or opposite value to store different kind of values. Then USB drives, and later of course solid-state disks. And solid-state disks, because here Moore's law still applies, it can be miniaturized or made smaller and smaller. Therefore all mobile devices and high-end devices switch from magnetic disks to solid-state disks because it is smaller. And maybe with time it will become cheaper. And also a good thing about solid-state disks is that they do not have latency as big as for hard disks, because you don't need to wait while this plate of disk rotates in proper positions that the read-write head can either read or write data for it. It still has small latency because it relies on some physical process, how you change these bits inside it or how you read these bits, but these latencies are much smaller in solid-state disks than in hard disks. But still all these rules apply, that different levels of memory, fastest one is the most expensive one, and the cheapest one is the slowest one. And we can demonstrate it with something like this. So, what I have created before this session, I created so-called RAM disk on my computer. And it is under folder /RAM disk. And that means that some part of my random access memory I'm using as a virtual disk to read-write files into it. It was very popular in old school computers when you needed to read something from audio cassettes, which were very slow comparing to today. And then if your computer had enough memory, you could say that some part. So how does it work? Example here, I have approximately 8 GB of random access memory. And I have told on my computer that 2 GB will be RAM disk. This means if I write to this folder /RAM disk in my operating system, what actually happens is that for this reserved part of memory, I read and write some values, whatever I like to write, inside random access memory. Then I have solid state disk, which is, I do not know, I think approximately 500 gigabytes. And then I have USB disk, which has, I do not know, maybe 16 gigabytes in size to store. And these of course are not to scale. And so this one is the most expensive one, this is a little bit cheaper, and this is the cheapest one, but this is the most fastest one, this is slower, and this is slower. And what can we do? Here we will talk about command line in more details later, but Linux is very great for different kind of silly experiments and exercises, etc. With this command I'm doing following thing. It's not even much of a program. I call two utilities. Time utility counts time, how long something was invoked. DD utility is disk duplicate utility, which you can use to duplicate disks very quickly. But in this case, input will be specific device called 0. So if you read, for example, I need to say how many bytes. So for this device I can read as many zeros as I like. And here output will be this RAM disk folder, which is actually located in random access memory, not on my hard disk. And I will write, I do not know, 1 million of 4 kilobyte blocks inside this memory. And if I execute it, you see that here I actually read it from device provided by processor, which just reads zeros. It's 0 bytes. So it wrote everything in approximately 0.9 seconds. Maybe it can be done even faster. With approximately 400 megabytes per second. But it depends on how many things my computer is also doing. For example, here I'm running virtual machine, I'm running Zoom session. When I didn't have everything else running there, typical speed was 1.5 gigabytes per second. So that's how quickly this random access memory works. If I do the same and write in my solid state disk, executed it as a user. So now speed is approximately 200 bytes, and for magnetic disk that would be maybe 5-10 times slower. And of course it depends what operations are working there. And third one is to read write into USB disk, so I have inserted USB drive in my computer, and location for it is following. And if I try to, and here you see million here, and only 1000 here, because it's much slower. And you see that speed is approximately maybe up to 15 megabytes per second. So random access memory up to 1.5 gigabytes per second, solid state disk maybe 200 something megabytes per second, USB stick maybe 20 megabytes per second. So, and therefore, if you need to create some copies of your family movies and thousands of photos for your wedding or whatever, then of course storing it on external devices might take quite a lot of time. So that's about these different kinds of memories. Now more details about buses. So bus in general is just a bunch of wires connecting one device to another. So you may have one device to another device, and then you connect it with other. And for bus, there is no straight borderline between buses and like networks, but in general what is important about buses is that usually they have at least two distinct lines for instructions to refer to memory lines and data lines. What does it mean? For example, if you read it right from or to memory, then you may have here, if it's parallel bus, for example, lines to refer to particular cell in memory. For example, you want to write something from this cell of memory, your data line would be 0, 0, 0, 0, 0, 1 here, 0, 0, 0, 0, 0, and 0, 1, 0, 0, 0, 0 here. That would be separate memory lines. And then you need to read actual value for it. Value lines. And if you actually can read and write not only a single bit but several bits, then you start, for example, referring to memory in this place, and you can read several values at once. For example, 0, 1, blah, 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 for value lines. And so usually, where is the difference between network and bus is that even for these buses which are serial, they still have distinction between how you refer where you want to read or write, or to which device you refer to using its address, and then separate lines for values. And initially, for most of computers, when you wanted to have big speed, you used parallel buses. And what means parallel buses? This means you have many parallel wires connected to devices, many lines to say which particular address you are referring to, and many lines to read several bits at once. So, typical example do we have? For example, for parallel communication, you have these bands of wires here, because you have to send several bits at once to refer to particular cell in memory, and several wires here to read and write several bits at once. So that was initially, but problem was that as speed for these buses become faster and faster, problem is about synchronization. Because if you look on lifetime of such parallel bus, so here is time is flowing, and here are several memory lines, and here are several data lines. Everything has to be very synchronized in time to know when it says 0 and when it says 1. For example, if these memory lines change from 0 to 1, from 0 to 1 somehow, and as I change from 0 to 1 to 0 to 1 somehow, as I change from 0 to 1 somehow, and as I change from 0 to 1. So to read specific zeros and ones, these bits here, synchronization is very crucial, that when these are changing, these changes becomes outside or inside proper one when you have this particular, and here you have some synchronization ticks, when you actually are allowed to read values for memory lines and for data lines. And as speed for this bus becomes bigger and bigger, so this means time becomes shorter and shorter, then actual length and length difference for these wires becomes more and more important, and therefore in theory parallel bus always should be faster than serial bus, because you can send more data at once. So here, when you write, for example, 8 bits at once, it is 8 times faster than writing just single bit. But problem is synchronization, and therefore usually parallel buses are today used only to connect like processor with random access memory directly, and it's almost that's it, nothing else. And everything else is provided by serial bus. And in serial bus, in theory, you need only 2 wires. One is ground, common ground, and another is signal. And then in signal you say with some particular thing, like 3 bits together here, this will be address, and then you put some address here, and then particular stamp to signal that now these are data, and then these are data. So you multiplex where you want to read and write something with some signature and bits to say I want to read or write from this place, and then sequentially you say that what you have read or write into this data are another bits here. So everything comes, and of course these values, the low and high, can be represented as zeros and ones. But in reality, life is more complicated than that. Usually you still may have different kind of utility things, something like ready and steady or whatever. So it still usually has, for example, typical serial bus for hard disk drives is SATA, and it has, I think, 8 lines in total. What these lines are, I don't remember because I never knew exactly, but still it is considered a serial bus because it doesn't send many bits in parallel, but it sends bits in sequence in time, during time, but all these additional lines are just for different kind of utility purposes, etc. So in general, parallel buses initially were used where you needed high performance, but that was relative high performance. Today only parallel bus which is still living in personal computers is connection between processor and random access memory, because there of course speed is crucial, and size is small because everything is put quite close together. For everything else, serial buses are used because it is much less resistant to errors because you do not have such problems with synchronization of parallel signals in the same time. And what are main buses used today? For example, for external devices, Universal Serial Bus is leading standard. For internal disk drives, including solid-state disks, SATA is coming from Serial Advanced Technology Attachment, and then there may be different kind of things. And for example, different kind of external devices, today you mostly connect using USB, or if you are using personal computer or compatible to personal computer. If you are Mac users, then of course they are legendary and famous with their own proprietary standards. They use the same principles like USB, but claim that they made it better. Definitely it's made different, and like FireWire standard for Apple is approximately the same as USB version 3. And so you connect all external devices mostly using USB standard, but of course there are proprietary standards, for example DVI bus for mostly for graphical displays. In theory it can be used also to read-write data for DVD players as well, etc. And yeah, so I thought there should be. So, and one of issues for these buses is that you need to have precise clocks, and there are many clocks in modern computers, not only to clock frequency of central processor, but for many other things. And important part about parallel buses is that all these data signals should be very nicely synchronized with this internal clock signal sent through this bus as well. And as faster this bus becomes and as longer wires you have, as more problems it makes. And for example here is, I think it's some kind of printer adapter for parallel bus, and this is serial bus. And remember, even though for example USB has 4 wires inside it, it is just 2 wires in one direction, 2 wires in another direction, so it is still serial bus, not a parallel bus. So minimum amount of wires in serial bus would be only 2, but for example for this duplex mode is that one device sends, another device receives simultaneously. You have 2 pairs of these wires, and then you may have even more. But in general, cables for parallel buses look like this, and cables for serial buses look like this. And particularly for USB, what is important is that it is de facto standard for many external devices for computer. Only problem is that there are 3 different versions of USB which are not absolutely compatible. And for example in your computer you may see that some of USB sockets are black and some of these sockets are blue, and blue ones says that it supports USB standard 3, which is faster speed, and if it's black then it supports USB standard 2, which is slower one. Probably neither of your devices uses USB standard 1 anymore. And then there are other buses, for example DVI, as I told, for example for displays, which is either digital or analog, and HDMI, which is proprietary, so everybody who implements the standard how to pay royalty or license to use it. And then there may be, for example, this IEEE 1394 initially made as a FireWire standard made by Apple with on Thunderbolt, and one of these is compatible in general, very similar to USB standard 3. Of course, plugs and sockets are completely different. What is interesting about Thunderbolt interface is that it was first interface because Apple is famous, at least they claim, about usability and user satisfaction. There are hundreds of memes about USB, which you have to rotate twice to get it right because it doesn't fit. You rotate it 180 degrees, still doesn't fit, and you rotate it again, and only then it fits. So Apple introduced first actual plug and socket, which is symmetric, so you don't need to rotate it once or twice to fit into it. And of course, USB 3 with this Type-C adapter also uses the same features, that it is symmetric, so it actually has duplicated connections in one side and another side, and to allow you to put this plug into any way you like. So, and that would be about the hardware. And now we will go to software, and before we go into break, there may be some questions or comments from you. Okay, so before we go forward, I thought about this in this break, and I actually wanted to show a little bit more about endianness of processors. So where was I? So one of things that I told you is, if you are a sloppy programmer and you forgot that you have to read 4 bytes instead of just 1 byte, and then you may get error for these properly built big endian systems, because if you will write first byte from 4 bytes which you had to read, you will get completely different value just to read 1, 2, 3, 4 or any small number than for little endian systems. But it's even more serious than that sometimes you may even lose some data because of types of numbers and systems what your computer can hold. And for example, here I'm using terminal to interact with a computer using text on my own local computer. I'm Valdis Atoto, and because it's short, nice name to call my computer. And if I check, for example, how many bits this processor on my computer can handle in Unix-based systems, you can get this information in command line by getting content of virtual file and file system of your computer /prots/CPU info. So we see it's genuine Intel processor. Its model name is Intel E5 blah blah blah. It supports following features, and somewhere here, it says how many bits it can handle at once. This is just cache. But you see that it's 64-bit processor. And when I created this test file here, this very long integer actually is 8 bytes. On 8 by 8 it is 64 bits to hold this value. And that means for 64-bit processor everything works more or less okay. For example, if you have long integer read just one first bit for small endian systems, you will still get proper value. But on my home office I also have home router, which is based on Raspberry Pi. And its processor is completely different. So processor is ARM version 7, blah blah blah. And what is important here, that it can handle only 32 bits at once, not 64. And if I create the same test file on that computer and compile it, I get warning here that I got overflow of my integer type because this long E is overflown. And when I run this program, what I got here is only first part or 32 bits or 4 bytes on this very long number. But if I would write something different here in this file, like just small value, so I'm sloppy programmer, I don't know that this particular So I'm sloppy programmer, I don't know that this particular computer actually cannot handle so long numbers. It can handle only twice as short, but I store very small value in it, just let's say 1. And I execute it. And you see here that all these data still hold up, because with this little endian system, what was overflown and actually not used was just zeros for me. And so I can update it till to something like and this also should work. Because now, even though this number is shortened and I'm using smaller values than I actually need to store these values, everything still works. And 30 years ago, when quality assurance was not so good and importance for programs not so good, many of programmers were quite excited about these things. And they decided that this wrong order of representing bytes into numbers is actually a good thing, because here, even though my computer, this home router on Raspberry Pi, works completely differently, its internal structure is different, but it's also a little endian system, even though it got this overflow and cannot handle such large numbers until actual values are actually smaller than I have declared here, everything still works pretty fine. And that's also why little endian systems are used, which stores order of bytes in proper order. Other thing, before we go into software, is about buses, what you can do to inspect your computer. In Microsoft Windows and MacOS, you have different kind of proprietary graphical tools which you don't know how they work, and you can learn how to use them only for the same system, same computer, same operating system running. But for Linux-based systems, there are quite a lot of different utilities which you can use to inspect your computer in absolutely the same way. For example, here is terminal on my own local computer. Here is terminal where I have connected to server of website odo.lv. And here is terminal on my home router running on Raspberry Pi. So one thing you should already know, for example, CPU. Not props. So these things when you can inspect. But similarly we can inspect things related to buses. And those of you who have worked with Unix-like systems like MacOS, etc., you know that list is shortened as ls and it shows files. But particularly for Linux, they extended this meaning of ls to more other commands. And there is command, for example, list devices, which shows what kind of devices I have inside my computer. It will probably not work in every system because it is not installed by default on other Linux-based distributions. So, and then you can see, and I think there's also more verbose variant for it, where you can check what kind of devices your computer has, how do you address referring to particular device and what address range they have, etc. Then there is ls block devices, and block devices are devices which are addressed by blocks. I cannot tell this to you. So when you talk about addressing, I told you that, for example, random access memory is addressed by one single byte or 8 bits. And that's how you can address some value inside it and store. And if you, for example, need to store only bits, true, false, true, false, true, false, then you need to do some more aggregation. For example, to say that you will read from this byte only second or third bit in that thing. And most of devices which uses addressing, so they allow you to read and write from several places in the memory, are addressing using 8 bits or 1 byte. And in general, these are called char devices. Why char? Because in C programming language, char type is one single byte. And because initially many of these devices actually send characters forward and backward. And you should know that character is abstraction from letters, numbers, punctuation mark, and control characters. And all these fits into these 8 bits. And for sequential devices you can just read write character by character by character, but you may refer, for example, to random access memory as a character device where you can read write characters in any place you like by referring inside it. But then there are other devices which are not char devices but block devices. And what is important about block devices is that singlest addressable unit of memory is not char, but it's block. And how large block is, it depends on many parameters. And typical block device is either magnetic disk, hard disk in short, or SSD disk. And if it happens that you still have 32-bit operating system running on your computer, 2 in power of 32 is approximately 4 gig or precisely gigabit addresses. So in 32-bit operating system you cannot refer to larger address space to write something from cell than 4 gigabytes of data. But if you have, for example, 1 terabyte of hard disk, then question arises, how can you actually use so large disk if only thing what is allowed in your operating system is just 4 billions of unique addresses? And so you do not refer to addressable units in hard disk just by single byte or character. You refer to it with blocks. And for example, if you have 1 terabyte, so that means your block will be, I think, kilo, mega, giga, tera, will be 1 maybe byte of data, or approximately 1 million, or precisely 1,024,000 blah blah blah. So that means that smallest amount of data you can read-write from your block device, like hard disk, is 1 megabyte of data. And if you have not many files, you like how legal or illegal movies on your 1 terabyte disk with your 32-bit operating system, then that's okay, because you will have many megabytes of single file. So that means you will have block here. Each of block is 1 megabyte, and you will say my file starts here in my block device and starts with some block here. And of course, if you have fragments, these are fragments not sequentially after that, but distribute in entire disk, etc. But if you will need to write just 1 single bit inside your file of block device, it still will use entire 1 megabyte of block just to store 1 single bit here, because you can't refer to particular place in your block device as just 1 particular block. And of course it's not problem for 64-bit operating system, because it allows you to address 2 in power of 64 unique addresses. And because of speed, so these blocks may be much smaller, even for terabyte devices, but usually it is approximately 1 kilobyte of data, actually binary kibibyte. So again, if you still need to store 1 single bit in your block device, then your file will still contain 1 kilobyte of data on the disk because you can't address less memory amount on block device than one single block. And so this list block devices shows you what kind of block devices you have on your computer if you run Linux-based operating system. And of course, block devices for my computer are only different kind of disks. This is built-in hard disk with several partitions. And this is this USB stick still connected to my computer. And if you want to see detailed information, for example, how large this block is, I do not know what is precise flag for it, but -O shows all the data. And somewhere here it should say what size of block this device has, and I will not be surprised that some of these numbers, 512, is size of block for this particular device. Flux, serial size. Some of these properties shows what is block device for these particular block devices. So that's one thing, you can list block devices. You can also list these parallel communication devices using LSPCI. So PCI is one of these buses you use inside computer to send data concurrently or in parallel. Actually, there are two PCI devices, serial PCI called Express PCI and just PCI, which is parallel. And I do not know, though it shows all these. So these are internally connected devices in my computer. And what I see here, for example, graphical display is using this bus USB controller, so it connects all other USB devices through this controller to be available to get it to the memory and processor. Memory controller, so that's how random access memory is connected. Ethernet controller for network, but it looks like no Wi-Fi controller, etc. And I don't know details, how to say, still similarly you can, for example, be very verbose about details of those devices. And what is important about these PCI devices is that, if you remember from previous lecture, I showed you this very simple computer emulated in web page, how we printed out this data just by writing some data inside memory. Of course, that computer supported only characters, no, not graphics, but similarly, these fast devices share some amount of memory which you can read or write, for example, to show input-output for graphical display. For example, for graphical display, if processor writes something at the range of memory starting key 000 till to D000, then what actually happens is that if processor writes data in this range of the memory, what actually is changing, pixels are changed into graphical display. So if it writes different kind of zeros, I will get black pixels. If it will write different kind of non-zeros, I will get different colors of pixels inside my display, what I see here on screen. Also, what is important is that not all devices are requiring processor to interact with memory. For example, for display it also has its graphical processing unit, which is specialized to do many things concurrently in parallel. For example, to show pixels on screen. And there are many devices which actually can read-write from random access memory directly without using central processing unit. So central processing unit may be busy calculating some numbers, something else, but display may be absolutely independently read-write something from memory, and so some part in memory which is not actually random access memory, but if I address, how to say it correctly, if central processing unit or this graphical processing unit access particular range of memory here, and it reads writes here, what actually is changing, it changes pixel in the graphical display. And these devices which can read write directly into random access memory are called direct memory access. So these devices may read write some data without using central processing unit at all. So, and all these fast devices, also for example hard disks and SSD disks, also actually can read write directly to random access memory without using central processing unit at all. So first, of course, you initialize how this memory is handled, etc. But when you read and write some data, if you don't need some general purpose calculations, just dump data from hard disk to random access memory, again, these devices may provide this data into memory without using processing unit at all. And so somewhere here, I do not know how it's shortened, these devices also should say, can they read write directly from random access memory or not. So and then there is LS-USB. And this is another list of devices connected to different bus, in this case in this universal serial bus. And again, we can look short list of devices like audio adapter, my touchpad for writing things, web camera, other audio devices, Wi-Fi adapter, and other things. And if you look on more details, then we can see more details about these things. And for example, in my Raspberry Pi based home router, it doesn't have all these utilities installed by default, but if you look on more serious device like, then all these utilities are installed by default. This is block devices, this is PCI devices, and this is USB devices. No USB device connected, of course, it is just a server. And yeah, interesting thing is that because Ethernet, this Ethernet is gigabit Ethernet, which is much faster than Wi-Fi support, is that Ethernet devices are using PCE bus, which is much faster. but Wi-Fi adapters are using USB bus because it's cheaper and slower, and for Wi-Fi connection it is good enough. So that's what I actually also wanted to say but forgot to say in first session. Now about software and connection from software to the actual hardware. Of course, nobody of us manages hardware directly. We manage hardware through the software, and that's our window how we can look in internal things, how computers actually work. And in most of cases, we don't even use utilities and things coming from operating system directly, but we use different kind of applications. You may look on Wikipedia about proper naming convention, what application means, but in my simplified declaration, application is program or software used by real user, by human. So we actually use our hardware through different kind of applications. Then these applications use different kind of services provided by operating systems. There will be some layer in between them, different kind of libraries, utilities, etc. And only then we actually manage actual hardware, processor, memory, connected devices, etc. And so in high abstraction layer it looks like this, that user use different kind of application software or applications or apps. In short, these apps uses resources and utilities and things provided by operating system, and only then actual hardware is used. And for this part, software is very important because that's how we actually see, manage and look on hardware. So what is software? From this one Neumann point of perspective, software is just data which you try to execute, and if these data have proper instructions for execution, then it even works. If they do not have proper instructions, either it fails or does something else. For example, you think that you opened word processor, but what is happening in background, your computer is mining bitcoins or is sending too many pings to Microsoft.com or whatever website. And so software in general is just connection of instructions of computer to do. For different computers, of course, actual instructions are different. And software in general is just collection of different kind of programs. And computer programmer or software developer or coder is person who creates different kind of programs or software. And to write this software, you have to use programming languages. And programming language is easy way how you describe instructions for your computer. All computers are just reading numbers, and depending on numbers what they read, the internal switches change compositions, and these numbers are added, multiplied, Boolean operations are done for them. They are loaded and stored from memory, but in most of cases you are not interested about such low-level operations. You are mostly interested about little bit higher operations, like at least the saying multiply this number by this number, remember this number and do something with that number. So such programming languages are called higher level programming language. So as closer language is to machine language as it is considered the lower level, and the lowest level, which is still readable, for humans is a language called assembly, and that uses short mnemonic representations of these operations. How do you operate with these numbers inside computer, and then translation from assembly programming language to actual numbers which will be used as instructions for processor is pretty straightforward. In most of cases it's just one-to-one relation. One word in assembly language is one number inside machine code instructions. But in higher level programming languages, they can describe it in very different ways, and it depends on how high level this programming language is. And if these are general purpose programming language, this high level is usually about variables which you assign and remember and use operations with these variables, and then you can put these things together with some structured date, and you do something with structured date, etc. And for example, if you look on how actually computers work, they read just binary numbers from memory and execute them, and of course it is not readable and understandable for any non-trivial computer. Of course, that was how these initial computers built 60 years ago were programmed, but of course their features and possibilities were much smaller than for today's computers. And therefore closest programming language which is still used today when you actually need to interact with hardware, for example, your responsibility is to write device drivers or programs which drives your devices, like graphical card, network card, and processor itself, to do some data. So you write these instructions in assembly language, and assembly languages are specialized because for each different hardware, for each different architecture like processor type and chipset which is around this processor, this assembly language may be different. Of course, most of influence for assembly programming language is type of processor, but then there may be some limitations what you can or what you cannot do with memory inside particular computer. And so you write, because you have to write, why today's assembler is still not very readable, because remember, I will show you it in demonstration, that you have to write very many commands to do just quite simple tasks, and because you may get tired of writing these many commands to just add two different numbers and save them in memory, all these assembly languages still use very short abbreviations of these commands because length of these is quite long. And for example, to load some number from register, you say, for example, load accumulator, then add it from number in register 0B, and then store this accumulator in register 0A again. And so, but in high level languages, in general purpose language, you do something like this current balance is current balance plus new value here. So, and it is much easier to understand, and of course when you translate it into assembly programming language, it becomes much longer. And then there is no precise border between different kind of programming language, but still there are two general programming languages in the world. One is called interpreted and another is called compiled. And where is difference? for compiled programming language, you never execute your source code itself. So you write something into text using whatever programming language you use. And then, if it's compiled programming language, you transform this text file into different file, which actually will be executed. And so this translation from text to series of instructions for computer is called compilation. But then, if you are not so interested about speed, you just want to make things quick enough and get things done, then you may use interpreted programming languages where there is no actual file where these instructions are stored in compact form. For interpreted programming languages, it happens something like this. For compiler, you have text, then you compile it, and then you have let's say instructions, and then you execute. But for interpreted languages, you have text, and then you run interpreter, which reads text line by line and executes it on the fly. And there are some places in between, like Java programming language and compiled Python, where the interpreter do not read text, but it reads so-called bytecode, but it is somewhere in between of actually really compiled languages and interpreted programming languages. And why these two approaches still exist? They exist because of speed consideration. So we can go back to our demonstration. And here I will show you, you don't need to understand everything about language itself, but you just need to trust me that here is interpreted programming language called shell script used, which does following. It runs into infinite loop, and it prints out hello world, and it runs it forever until I stop it. And this is interpreted programming language. So how can I execute it? I can't say like hello sh. I can if I add executable bit, but what actually will happen is that I run another process called bash command line interpreter, and then it is executing this script. And if I open another command line utility which shows activity of my computer, I see that now one of the most active processes on top of used resources is this bash command line interpreter, which prints out this hello world. So what I'm actually executing is this interpreter. And there is no difference if I will say that allow to execute my hello sh, and I will call it directly, but it is still just text file. And if I add permission to execute it as a program, what actually happens is that this is just for my convenience, to make it easier. I run it, and I still see that there is hello.sh now, but if I will check what parent of this process is, when I check on processes, I see that still this bash command line interpreter is invoked, and then it invokes this hello sh text. So it reads it one by line and then executes it depending on what was written there. So that's about interpreted programming languages. Then there are some programming languages in between, like Java programming language, which does the same, only Java is much verbose programming language than Bash. So I need to declare class hello, I need to declare entry point for it, but when it starts it does the same. It runs forever until I interrupt it, and it prints out hello world in standard output in output in terminal. I have to compile it. And when I have compiled, so Java C is Java compiler, and then I have to run Java virtual machine, which you may say it's still interpreter, but it's not, because proper interpreter is executable file which reads text file and executes it. But if we check what we have provided with this compiler, it is not text file anymore, it is binary instructions, which of course has some strings inside it for execution. So it's not interpreter anymore, because proper interpreter reads text and executes it. But Java virtual machine reads binary instructions, but it's still not directly executable. Again, you may add execution permissions to this file, and you may try to run it, but now it tries to run it with bash command line interpreter. So what you need to do is you call another process, this interpreter or Java virtual machine, and we see that we have run Java virtual machine and then this script. And when we check what is top processes running here, we see that now this is Java virtual machine running in my computer. And then there are properly compiled programming languages like C, which does absolutely the same. It runs into infinite loop and prints out hello world. And of course we have to compile it. Let's say output will be hello. And then this we can run directly. And if I see what is top process here, I see that now actually this hello is running as a actual instruction what is running inside my computer. So this is properly compiled programming language, because I created another executable file, which means I have this set of instructions inside it to be run in my computer directly. And if we look on internal structure of this file, we see here my refresh doesn't work. this one. So here are these binary instructions which are directly executed as numbers inside processor of my computer. And now, why all these three languages exist? Because interpreted languages are much easier to use, but they are the slowest ones. And what can we do? I still think this RAM disk created, which is virtual hard disk inside my random access memory. Let's remove the 0 file and we can check how fast they are. First, let's say bash and run hello sh, and I will redirect output to this RAM disk hello file, and I will check how long it works as well. So it worked approximately 5 seconds, 6 seconds. And during that time it wrote 90 megabytes of hello inside this file. If you don't trust me, see, that's the entire content of this 90 megabytes. So that's for this Bash interpreted programming language. If we do it with this Java, implementation, approximately 6 seconds again, and I now wrote 30 megabytes of hello world inside this file. But if we use properly compiled programming language, it will work a little bit longer. You see that I almost, okay, let's try it again. Of RAM disk, free RAM disk, because there is only 2 gigabytes of data inside it. You see that it wrote 1.3 gigabytes of data inside this RAM disk. Of course, and you see that cleanly interpreted programming language is the slowest one, then like Java, which is halfway through compiled programming language, it converts text into binary data into numbers for execution, but it's still not executed directly. There is this Java virtual machine which reads these instructions and executes, and then properly compiled programming language which you can execute directly inside particular operating system. But sometimes it's not so important, because if you write it to the slow device, it's not so important anymore. For example, if we use some slower device, like my 16 gigabytes of USB stick, and we check, for example, on slower device, 14 megabytes. (18 MB with Java. And with this actually binary, hello. It's too fast and too busy, do not want to stop. Let's redo it again. And you see, it worked twice as long, 57 megabytes. And that's why different kind of programming language still exists. If this bottleneck or slowest place is actual execution of your program, and everything else is fast enough, so it's not the bottleneck or slowest place, then of course it is very important that you use compiled programming languages, because then these instructions work much faster and you get big speed improvements. But if you are working with some slow device, like my USB stick, there is some differences. For example, Bash only 14 megabytes, Java 18 megabytes, and binary application in C, let's say 25 megabytes. But this speed improvement is not so big, because the slowest thing and narrowest place for data handling is not actual application or this program I'm executing, but device I'm using. And therefore, if you are working with comparatively slow devices and your scripts are efficient enough, etc., then of course these speed differences are not so important. Remember, when we worked with fast device like virtual disk inside random access memory, difference is approximately 1,000,000 times. Maybe not full million, let's say 500 or 100,000 times. But here with slower devices there is difference, but it's only 1, 2, 3, 4 times. And so in such cases this is not so important anymore. And so when you look on most popular programming languages, so Python is interpreted programming language. You may create Python programs similarly to Java programs which are partially compiled, so text is converted into more effective and efficient form in binary data. But only difference is that this interpreter do not need to convert text into instructions anymore. It reads instructions and executes, but there is still this process which reads instruction and which is not executed directly into a particular platform. Java is semi-compiled programming language which compiles not to actual hardware but to so-called virtual machine, which is abstraction of real hardware. JavaScript is interpreted programming language, C# compiled, PHP interpreted programming language, C or C++ compiled programming language, R interpreted programming language, Objective-C compiled, Swift compiled, TypeScript interpreted programming language. And so how this compilation works? So we may go back to this previous example. Of this C debugger, and we may open, let's say, Control C, and okay, let's take this one. So this is in compiled programming language, and in this case it is C. And I showed you, for example, how it looks, at least one part of it inside memory. And of course you may see here, when you look on these numbers, probably sooner or later you will see some similarities between numbers in this window and that window. But particularly GCC also allows you to check how this would look like in assembly programming language. For example, when you need to say execution of my program will start here, in assembly programming language, I have to say something like this. Put something in this place, move something from here to here, and call execution from here. Then, when I declare this variable, in assembly it looks like this. Then, when I declare another variable, in assembly it looks like this, and then in assembly for this cycle, then here printing something out takes quite a lot of space because many internal procedures are, and here it should go back to some previous sequence here. So that's how would look this program if I would write everything in assembly. And actually I think I can create so here is the same program rewritten or translated into assembly programming language, if I like. So it doesn't mean that all compilers can rewrite for example high-level programming language in low level, particularly GNU C compiler actually compiles directly to these machine instructions into numbers, but it can use as a side product also convert these numbers into assembly programming language if you like. So this is not intermediate step, it is step for debugging. For example, these who need to work directly with hardware, with devices, for them it's easier to read this one than machine instructions, just these hexadecimal numbers somewhere here. So that's about compilers. So most of compilers convert this text into machine code. Some compilers may use like assembly language as intermediate language. In general, compiler is program which converts high-level programming language into lower-level programming language. In most of cases, this lower-level programming language is machine instructions themselves, but there may be some other tools which use it differently, that you have one programming language converted to another, then to another, and only then to actually executed machine code. And so this is in general how these compilers work and then later, if we will have enough time during other activities as well, we will have one session also to learn some basics about some particular programming language, and definitely it will be some of high-level programming languages, which probably is the most useful one. I cannot say which one particularly, therefore I will not promise anything yet. But so in general, we manage our computers through the software, through the programs. So we describe our problem in some kind of programming language. We try to use as high level programming language as possible, because that is the most efficient way in terms of development. One also important thing is that in general, if you care about execution speed, what I showed here in this comparison of hello applications, you try to write these applications as low programming language as possible, closest to the hardware, because in such way, if you manage it directly, you can get most of hardware directly by your applications. Problem is that all these applications are hard to write, and therefore you usually use such low-level programming languages only if higher level programming languages are not fast enough. But in general, if you do need to do heavy calculations and narrowest place is speed of processor and speed of your calculation, then still the best result you may get by writing this code as close to hardware as you can, because it will be faster. But as processors and computers become cheaper and cheaper, so in 1960s, 1970s, computer time was much more expensive than programmer's time, and therefore programmers optimized for speed of execution, because bunch of programmers cost less for company than single busy computer. But today, when hardware become much cheaper and computer time is less expensive, in most of cases we optimize software for programmer's time, not computer time, because any time you look on your used resources in your computer and you see that your computer is mostly sleeping, doing nothing, you don't need to optimize it for speed of execution. You need to optimize only if all my 4 processors of my machine are 100% busy and it still doesn't work quick enough. So therefore, today in most of cases, all programs are optimized for speed of development and developer's time, not computer's time, because computer's time in most of cases is not bottleneck anymore, because it is less expensive to develop something in high-level programming languages and just spend a little bit more money on used electricity, used network bandwidth and used hardware than to pay for a big bunch of developers to somehow optimize this application to run a bit faster. So therefore, when you start with dealing with problem, you usually use the most easy programming language possible, and only then, when it has proved that it doesn't work quick enough, then you can change to different programming language. And there have been many projects also in open source world when they start with high-level programming languages, interpreted programming language, and then when problem is understood and it works, but it doesn't work quick enough, then this code is rewritten in different programming languages. And here again, the other tools may come into. So compiler is program which takes most of time text as an input and provides lower level output. So this is input, output. That is compiler. But sometimes in some projects you may use tools which are called transpilers. And what transpiler does, it uses text as an input and text as an output. But only difference is that this text may be, I do not know, Bash script or Python, and this output is like a C programming language. And then you may compile it and it will be with compiler and it will work much faster. So before you start writing something, you may start with very high concepts. You do not care about programming languages at all. You just describe business process. For example, you can draw just different kind of flow charts and diagrams how this business process should go. In most of cases, you do not write this process as easy as counting from 1 to 0 or not 1 to 0, from 0 to 100 or something like this. But if the talk is about some kind of business process, some website for web shop and finance system, etc., then you may just start with very high level concepts. You do not care about programming languages at all. You just describe what process should be automated, what should be done in this particular system, and only then you can start writing it. Also, you may write it as a pseudocode. So this is pseudocode is used when you need more formal language than like general English, but you still do not care about actual programming language, what you will use in actual implementation. So then you take out only precise subset of general English and then describe it in so-called pseudocode, which is formal description than that would be in just basic English. And then you may look into different kind of programming languages. First decision is speed, execution speed consideration. And if your application runs in networked solution, if your application reads writes something from hard disk, if it reads writes from keyboard and mouse, so it interacts with human, then in many cases speed is not consideration, because slowest device is either human or network or hard disk or whatever, and then you decide to use that programming language which is easiest to use in this particular case. And then you plan for it, then you design, and then you design a little bit more, and then you actually write and test it and release it. And important part about this high-level program, and then there are different kind of specialized programming languages called domain-specific languages, or DSL. So Java and Bash are high-level programming languages, but these are general purposes programming languages. So they are not very specialized, and you may be as inefficient in Java as Bash, for example, to writing application for financing, etc. But then there are these domain-specific languages, and for example R is one of domain-specific languages, and this is about arithmetics and number calculations. And this is one of these domain-specific languages. It is very efficient if you need to handle large numbers, and because many companies today have access to very large data, so-called big data. And big data are data which are either big or changes very quickly or is not structured very well. Then you have different kind of problems dealing with them. For example, you have gigabytes of poorly structured data like tweets or whatever for Twitter, or different data for Amazon or Facebook or Google. Then you can use R as a domain-specific language to deal with these large numbers more efficiently than, for example, using general-purpose language like C, Java, or Python. And so that's one of important things to remember, that all this software, what is written for now, becomes more and more complicated. And without high-level abstractions, with more specialized programming languages to deal well with this particular case, this pork becomes just too complicated and too enormous to actually be implemented in the software. So neither of today's widely used software, including spreadsheets, text editors, web servers, web browsers, websites, etc., cannot be actually implemented in low-level programming language like assembler. But they can be implemented and are implemented in high-level programming languages, because then you can do more writing less code. And software development is one of important problems in today's IT world, and dealing with complexity is one of important factors. And one of managers and computer scientists who paid attention first to this is Fred Brooks. He was manager of mainframe computer, development of mainframe computer called IBM 360. So IBM 360 is real computer, big endian system, multiple users, took large room for it, and so he was one of first who, and they developed both hardware and also software or operating system to run for this hardware. And it was the most complicated software at that time, and it was quite challenging project at that time. And it introduced this rule called Brooks law that adding more manpower to a light software makes it even lighter. And also his contribution to computers is that at that time, it was 1960s, memory was still very expensive, and initially they decided that only 6 bits would be enough to handle enough characters for input-output for computers. So that means all capital letters, all capital Latin letters, sum of control characters and numbers, and that's it. But he made his contribution in computer history that he decided that it should be a little bit more future-proof, and that this computer should handle 8 bits at a time, not only 6 bits. So it first allowed lowercase letters to be included, and second, for this so-called extended Latin table, this also allowed to be included Unicode characters and UTF encoding schema for every other character because of these 2 free bits inside the character. So, and because of that, for example, ASCII standard is not changed for more than 40 years. So it's still compatible with modern computers. And then, before we go into details about software itself, here is just list of some price of failures when software doesn't work. So in general, hardware is harder to produce because it needs materials and it needs equipment like hardware to produce this hardware, like Intel and AMD fabrics which produces microprocessors, etc. But in general, these are much simpler than software because this complexity coming from software is converted into simplicity of the hardware by doing very, very many simple things in this hardware. And therefore, most of these expensive failures comes not from hardware problem, but from software problem. And probably you have heard something about year 2000 bug, when there was quite a large expenses for IT before year 2000, because many of computer systems at that time stored only 2 last numbers of year, and so for year 2000 it could be converted to year 0, not to 2000 after year 999. And then there may be other quite expensive bugs like for example, almost World War III happened because of a bug in alarm system for nuclear missiles, or for example for radiotherapy equipment, because of race conditions and bug in this several peoples were killed, because if this operator of hardware was very experienced and typed keyboard very fast, then it actually typed it faster than this device could respond, and so it went to wrong settings, and few of these patients got much bigger radioactive dose or radiation dose for their therapy and actually died. So that's about. And so as one of people said, Paul Ehrlich, is that to err is human, but to really fuck things up you need a computer, and probably computer connected to the internet. So because this happened a little bit faster than I expected, I can give you additional information when we finalize about hardware. And if you are curious and still do not understanding how hardware and software works, I recommend for you to look on two videos. One is very high abstraction level. Let's check this one. I'm not sure. Maybe this is proper one. Yeah, this is proper one. I will write it in chat. And then another lecture additionally maybe is this series of lectures about mega processor. So what is catch here? So problem with today's microcomputer is that everything is so small that you can't see it with naked eye, and you need to do different kind of abstractions like look on hardware through the software by assuming that through this software window you look on hardware properly. But in United Kingdom, some of these enthusiasts created absolute opposite of modern processor. So it's still quite modern processor, but it is implemented as big as possible that you actually can see. Maybe this is not. You can start. Very short overview. This probably one. And what is interesting about this lectures and series, that this processor is made in such a way that you actually can see every switch inside this mega processor as visible. So it shows input as a light, output as a light, and you can see how, for example, this arithmetical logical device works, how it converts inputs to outputs. So then maybe this also may be useful for you to understand better how it works. And for example here, so here it shows, for example, part of memory which is used to display. So it is small in terms of how many bits it can compute at once, but it's modern processor, so it supports also graphic, and you see that if it puts some ones here in memory cells as particular bits, it also can produce graphic on output display as well. So that's maybe additional information for you where you can look up about other things. So, do you have some questions or comments? Now I'm looking on chat.